Alright, time for another draftphysics.com, debatephysics.com, but I guess we ought to just call it debunkbadexperiments.com because that's all we're doing. That's all there is. They just keep trying to force their silly crap to match blah 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 blah. And it's just cheating, frankly. And that's the nature of people. And science is just as vulnerable. It's got a bunch of people willing to cheat the truth to sell their fables, their religion. All right, anyway. So, comment first, and then we'll do a dispar debunk. You say that mass of B doesn't affect the velocity of A. That's right. So you have two masses on either side of a spring, and the spring expands. And it's sort of the same argument as a rocket engine and all this other stuff, that you can't really stop the energy going one way with energy going the other way. You don't need something to push against, in theory. Now, with a mechanical spring, you can change that dynamic a little because you can actually move the explosion. That is, you can physically move the spring, which means it will expand in one direction more than the other direction because the spring is actually moving. All right, now the spring, it also has a limited capacity to expand. It doesn't expand at an infinite speed. So it has a mass. It's going to consume momentum by itself, moving a velocity. So at its maximum velocity, it's going to consume a certain amount of momentum just moving the metal of the spring. So yeah, they are not idealizations. So it doesn't matter how small you make B. Well, it does in fact matter, but it's not going to change much, is the truth of it. Now, how much it's going to matter, I don't know, but the fact is the spring is going to expand in that direction, and the other A object is still going to get pushed in this direction, and that's going to happen. It can be just one atom, and A will still gain the same velocity. So, again, we're arguing that the velocity it's going to gain is going to be substantially decided by which way the spring's mass moves. Now, obviously, if there's no mass on one side, the spring's mass will move in that direction. So it's going to lose some energy, no doubt about it. All right, but how much? It's what percentage? I can't give you the exact percentage. You have to know the difference between the spring's mass and the mass of the object it's pushing. Now, the greater that differential, the less the spring matters. What happens when you take the last atom of B away and there's nothing left? Yeah, well, then you have the mechanical limitations of the spring. The fact is the spring's not perfectly efficient. You're talking 80% efficient, and 85 maybe. Because it's actually expanding, and the lighter you make the objects you're pushing, the less efficient the spring becomes because the spring's using most of the momentum to move the metal of the spring. So the exact same subject comes up in the dispar debunk. So I'll get to that. I mean, if you're doing these experiments, you have to concede there's physical limitations. You have to try to understand the physical variables. The spring constant, isn't some kind of perfect thing. It's within limitations. Springs have a certain functionality, and you go outside that functionality, they no longer obey certain laws. All right. So I'll be back. All right. So this is just the visual. I'm not going to bother playing the video. It's absolute rubbish. He's videoing his camera's video. I mean, it's just all so bad. But I'll just go over the obvious flaws in the experiment. So you don't really need. So this is his outcome. So he has a range of 5.5 centimeters and 5.4, which is kind of huge considering, as I'm going to point out, that the weight of the lever he's using is a 3 here, probably at least, or a 4 itself. So the experiment, you're talking about this 1 centimeter of difference, and he's got almost a 10 centimeters of difference, and he's got a 0.4 centimeter difference in his outcome. So it's already going to be very suspect. So anyway, he's claiming that a 4 mass with 1 velocity has the same energy as a 1 mass with 2 velocity. It's nonsense, but whatever. Leave is draw it. Should be able to hit that button. And I did. Amazing. Okay, so drawing area. All right, so he's got, he's using a pendulum, a rigid bar, okay, as a pendulum. And, you know, theoretically, okay, there's no no crime in that. But with any lever, the idea is your weight, whatever you're going to swing on it, has to be much more massive, like 10x the mass of the lever, or else you're going to have to consider the mass of the lever itself. So, you know, when you say you put I'm going to compare a 5 to a 10, you know, let's just say you're going to make a comparison between two things swinging. You have to understand that your real center of mass is decided by how heavy this lever is. So if the lever itself is a 5, you can understand that the real center of mass is somewhere around here. You know, and in this case, it would be somewhere around here. So it's not the same experiment anymore. You're not testing a 10 against a 5. You're testing a 10 against a 15. So it's a very different experiment. So if you don't have the masses much heavier than the device you're using to swing it, obviously the experiment is going to be crap. All right, so he didn't do any of that. So what he has is a lever that probably weighs more than the weight he put on the levers. So it's, you know, obviously the difference is going to be fractional. So, and what he's doing is he's expanding a rubber band that's for some reason connected in some weird way here. But anyway, so he's taking a rubber band that's going straight across, and he's pushing it a certain amount of distance and measuring how much compression he gets out of it. Now again, we're back to the basic laws that yes, rubber bands have limitations like springs, so you have to know the constant of your rubber band in terms of what's its working range. A tiny bit of flex is going to be inaccurate, and too much compression, it's not going to be linear anymore either. So we don't have any of those details. And then the bigger problem, so what he should have done is first test the lever all by itself, right? So you put no weight on it, you swing it into the rubber band, and you see how much momentum the lever itself has, because it's a mass with a center of mass. The center of mass is going to get a velocity from the distance it's dropping, and it's going to create an impact. You're not measuring this if the lever weighs as much as this stuff weighs. So that's just the simple basic argument. Then the other problem is he's putting the masses on in this weird configuration where this is the lever looking down through the lever, and he's putting batteries, round objects, on it. And to do the form mass, he's piled a whole bunch of batteries around the lever, and so the surface he's pushing into the rubber bands is a different surface. Okay, it makes a difference whether this surface or this kind of surface hits the rubber band. If you pull the rubber band, you know, by having a whole bunch of the rubber band not stretched, then the part that has to stretch is going to have more compression in it because it's less rubber band to stretch. So, you know, if you have a full rubber band, easy to stretch. You have a half rubber band, harder to stretch. So obviously it's doing more work, but it won't be visual because you're not stretching the full distance. You really need to hit the rubber band with as small an object as possible. So whatever you're using as your mass, you want to have a part of it that hits the rubber band exactly the same regardless of the mass. So regardless of the shape of the mass, what hits the rubber band is the same in both cases. You have to do that. If your rubber band hits the other stuff and is deflected or changed, then you've changed the experiment. It's not, you're broken it. Okay, so what he's obviously done is, and he's doing this horrible measuring thing still, where instead of having a precise measurement, he's using a chart behind the object, you know, and just eyeballing it, when he should be using some kind of standard heights, you know, that are guaranteed each time to get the same exact amount of energy. But they won't do those kind of things because it's more work, and yeah, nobody likes to do more work. just a fact. But if you're going to be an experimentalist and you're going to prove physics, then you probably should pay your dues and do it with the precision the experiment requires. So I mean, it's just the premises are all wrong. There's no theory to defend what he's doing. He hasn't created a meaningless lever in the sense that the weight differentials are way too small. So the lever weighs this. The objects he's putting on him don't anywhere, not, like I said, it should be a 10-to-1, and he's probably not even 2-to-1. So the lever's doing most of the work, and the weights aren't doing enough, creating enough of a difference to really do the experiment. So if the lever has 60% of the momentum, then you only have the 40 to deal with, and then your measurements have to be even more precise. When you have the full 100, you can do a measurement, and you have lots of latitude. But if you take 60% off the ruler, and now you're only dealing with this little small fraction, it becomes necessary that you be more and more precise in everything you do. And clearly there was nothing precise in the experiment. Even the outcomes, again, two results, 5 centimeters and then 5.4 centimeters. I mean, those are huge differences in outcomes for exactly the same event. So there's nothing about his results that can be trusted in any way. Just another junk experiment. And this is getting old and tired and bullshit. It's just a waste of time. Debunking bad experiments is not what I planned on doing with my existence. So until they can show some integrity and do the experiments right, I'll just make my videos and say the hell with it. I mean, it's just pointless. I mean, these are silly premised arguments. I mean, again, Ian Gosling shooting things in the air, saying he's measuring how much energy it has when the objects aren't releasing any of their energy. And if you let them fall for 15 minutes instead of the tiny amount of distance to the height of the ground, the end result will be clearly still 2-to-1. But he just doesn't care about facts. All right, so let me see my mouse. Cost me $1.50. Anyway, so this piece of shit actually. It's actually quite good, except the scrolling wheel sucks. And the buttons are too easy to hit. But whatever. There's just no point. Okay, so until there's a point, till next time, hopefully there'll be something better to respond to, but I have my doubts.